Chapter 9, Problem 23. A 0.75 kilogram sheet is centered on a clothesline as shown in Figure 9-63. The clothesline on either side of the hanging sheet makes an angle of 3.5 degrees with the horizontal. This is downwards, right? So, because it's hanging sheet. Calculate the tension in the clothesline, ignoring its mass, on either side of the sheet. And the question is, why is the tension so much greater than the weight of the sheet? Essentially, why isn't the sheet, how can such a flimsy string, a small string, hold up a heavy, it's not that heavy of a sheet, but a weighty sheet? It does have some decent mass to it. Probably weighs about 7 newtons. So here we have the free body diagram of our situation. The clothesline, I essentially reduced the clothesline to a point mass just so we could talk about the forces it's feeling. So I have the two tensions at theta degrees above the horizontal. Yeah. Well, there's a couple ways to think about it, right? You could either have this horizontal and have it coming off of there, or either way. So yes, we have two tensions, both the same degrees, and then we have the weight. So we have to understand where the tension is coming from to understand what kind of factors build into the tension, what makes the tension the tension. So our handy dandy trick for this chapter has been to use Newton's second law. So we're using that again. And here we have basically just the sum of the forces in two directions, x and y, since it's a two-dimensional problem. And we see that there's only two x components, right? So we have one x component for T1 and we have one x component for T2. Now I'm going to let's define our coordinate system. Positive y is this direction, and sorry it's a little slanted, but imagine I made it line up with this. Maybe that's a little bit better. Forget about this part. So actually, can I get the eraser? No, yeah, let's not worry about it. So yes, I have a coordinate system here, and so T1 is going to have its x component in the positive x direction, while T2 has the negative component. Well, T2's x component is in the negative direction, I should say. So this just only tells us that they have the same tension in both directions, the clothesline, and so essentially the forces are canceling each other out. So we don't really notice this tension. So maybe it's more interesting to look at the y forces. So let's look at some of the forces in the y direction. Well, here both of the y components of T1 and T2 are positive, but we also have the weight going downwards. So it's a very simple equation. Let's see. Yeah, if you make a triangle here, you can see that this is the x component, this is the y component, and you just need to use sine to get to this y component. So both of them are going to be here, right? So just T1, this vector, times sine. And I'm not using vector symbols anywhere, but you can assume if it's a force or an acceleration, it should have some kind of arrow on it. But for the purposes of this, it's okay. Right, so summing the forces in the y direction, we have T1 multiplied by sine of 3.5 plus T2 multiplied by sine of 3.5 times sine of 3.5 degrees minus mg. And so to find T, we know that from the x condition that our tensions are essentially the same. Well, I don't know, I should say that our tensions are essentially the same, but no, yes, that's right. It does come out to that, because we should have taken this a little bit farther, maybe more. Should have had it down there, but taking this relation a little bit farther just shows us that Actually, yes, T1 does equal T2 here. So the bottom left the bottom left relation is correct, and we can essentially replace T1 and T2 in the sum of the forces of the y, in the sum of the y forces equation to give us 2t times sine of 3.5 degrees minus mg, and then t very clearly becomes 60 newtons after doing some algebra, just adding mg and then dividing by the factors on t. So we understand completely now why 60 newtons is the tension. The mass, there's three possible factors. We either have, because 1/2 is just a number, right? So we either have the mass, the acceleration due to gravity. Well, that's not going to change either, actually. So I should say it depends on the mass then and the angle. Those are the only things that can change, right? I mean, you could change gravity, but maybe not in this exercise. Um, so to put it succinctly, the angle is the main factor in causing the tension to be large. So I'll let you try this at home, but if you put in theta equal to 0, then the tension goes to infinity. So the smaller you make the angle, the tension becomes stronger and stronger. But if you held at a 90-degree angle, it would be half of the weight, and so the tension is just greater. The tension is greater than the sheet's weight because of this small angle. This makes a very big impact, especially when it's being divided by, because we already have the small angle approximation, which says that sine theta is about equal to theta. So if you're putting a small number in the denominator of something, dividing by a small number makes a big number, and well, the smaller you go, the bigger you go, right?